Welcome to this last video on Module 8, where we're going to be talking about something called statistical power. We're going to define statistical power, we're going to talk about some steps in determining that power, and then we're going to end up with some information about one-tailed versus two-tailed tests. So what is statistical power? It's the probability that your statistical test will correctly reject the null hypothesis. It's the probability that the test will identify a treatment effect if one really does exist. So power is the ability to find a treatment effect, but at the same time balance the risk of making a type 1 error. And this has a lot to do with our preset alpha and our sample size. So the first thing we're going to do when we're talking about powers, we're going to identify the treatment. What is it that we are studying? We're going to identify the null hypothesis, and we're going to locate the critical region. And these things will help us to determine statistical power. So statistical power is the proportion of the distribution that is beyond the critical boundary. It's that shaded area that we've been talking about. This we've been referring to it as the critical value or the critical region, the critical area. It's that shaded in portion of the distribution that we are considering for statistical significance. We can do power one of two different ways. We can load all of our power into one tail, and this is called a one-tailed test or a directional test. Or we can split up our power into two tails in a two-tailed test, or what we call a non-directional test. So what is the difference? Well, sometimes when I am conducting a study, I know very, very certainly maybe that my mean is going to be higher than the population mean, my mean of the sample. I'm not saying it's going to be statistically significant necessarily, but I know the direction that my mean will be in, whether it be higher or lower. I know which way it's going to go. And if I have an idea of where my mean might lie, I can do a one-tailed test. So if I think that the mean of my sample is going to be higher than the population mean, I can do a one-tailed test and load all of the alpha into the right tail. Or if I think that my mean is going to be less than the population mean, I can load all of my significance area or my alpha in the left tail. So this is called a one-tailed test. And this is different than the two-tailed test, where we kind of split up our alpha into two different tails because we're not 100% sure in which direction our result might be. It could be that I think that my intervention is going to increase the mean or have a higher score, but maybe it's going to be lower. I don't know that 100% for sure, so I do what's called a two-tailed test. Now, remember that I mentioned that the shaded area represents power. Which one of these tests has more power? Which one of these tests is more likely to detect a significant effect if one does exist? Well, it's going to be the one with more area in the critical region. So in a one-tailed test, we have 5% here. It's going to be easier for us to reject the null hypothesis. It's not such a great hurdle to get here as it is to get all the way over here to 1.96. So a one-tailed test is said to have more power, more ability to correctly reject the null. The two-tailed test has less power. So why would we do a two-tailed test? Well, we're going to talk a little bit more about that, but again, the main reason is going to be when I don't know exactly in which direction my result is going to be. So as the size of the treatment effect increases, statistical power also increases. So if I have more of a difference between my mean and the population mean, my statistical power increases. That I can't have a whole lot of control over as a researcher, but I can control some things in increasing statistical power, increasing the ability to detect a significant result correctly. So larger alpha is going to increase your power, 0.05 versus 0.01. We've talked a lot about 0.05 being sort of the standard alpha to use, and that balances our ability to detect a significant result while not making a type 1 error. Remember, a type 1 error is when we incorrectly reject the null hypothesis. We jump the gun. We say that something is statistically significant when in reality it's not. It's a type 1 error. So we want to have our alpha balanced. We want to have enough of an alpha that we're going to detect something, but not so much that we're going to open ourselves up to a whole lot of type 1 error. Now, a 0.01 is a very tiny area, isn't it? It's very small. So that decreases our chance of making a type 1 error, but it also decreases our power, our ability to detect a significant effect when one does exist. A one-tailed test has more power than a two-tailed test, and I just showed that to you because all of the alpha is loaded on one side, so the critical area is bigger. And finally, when we have larger sample sizes, we have more power than smaller sample sizes. This is just one more reason why we want to work with larger samples whenever possible. Going back to our illustration, we have a one-tailed test here with all of the alpha loaded in one tail, and the two-tailed test is split between two sides. As a reminder, if we look at 5% in the tail, we end up with a z-score of 1.645 or 1.65. And if we look for 2.5% in the tail, that equates to a negative z of negative 1.96 or a positive z of 1.96. So it's easier for me to have my sample mean be extreme in a one-tailed test than a two-tailed test. In a one-tailed test, I only have to exceed 1.65, but in a two-tailed test, I need to exceed either positive 1.96 or negative 1.96. So a one-tailed test, if we're going to do it, we have to state it a priori. So what does that mean? That means that I can't do a two-tailed test, find that I don't have a significant result, but I realize that if I did a one-tailed test, I would find significance. So I can't just rerun it in order to find significance. We only say a one-tailed test when we have a strong reason to believe that our mean might be in that one tail. So what is a strong reason? Well, it could be that we've read prior research that shows that that's probably where my result is going to be. Having a one-tailed test needs to be justified. You can't just do a one-tailed test just because it's got a larger critical area. We don't do that. We want to be as objective as possible and observe ethical guidelines, which involves setting your intention up front, either to do a one-tailed test or a two-tailed test, and then sticking to it. If there's no support for a one-tailed test, meaning no strong reason to think that my result is going to be in one tail or the other, then a two-tailed test should be used for sure. And one more note, you could choose to do a two-tailed test even if you have that strong reason to think it should be in one tail or the other. We do this in order to make it a more rigorous test. So that's perfectly acceptable. You can do a two-tailed test when a one-tailed test is warranted. But if you don't have support for a one-tailed test, you don't want to do the one-tailed test. Let's take a look at how we would write a hypothesis for a one-tailed test. First of all, a one-tailed test is called a directional hypothesis because we are proposing a direction that our sample mean will fall in. So when we are writing a one-tailed directional hypothesis, I highly recommend you start with the alternative hypothesis first. So that's right here with H subscript 1. And let's see what this hypothesis is actually saying. So what we have here is the mu symbol, and you're used to seeing that as the population mean, and it still is. But in this case, it means the population that our sample comes from, because we don't make hypotheses about samples, we make them about the populations that they come from. So in this case, it says that the mean of the population that our sample comes from is greater than the existing population mean of 80. The alternative hypothesis takes into account every other eventuality. So because we said in this first case that basically our sample mean is greater than 80, well, what are all the possibilities if it's not greater? Well, it can be less than 80, which I have here, but it also can be equal to 80. So the null hypothesis takes into account everything other than what the alternative hypothesis states. So let's take a look. We're going to find the critical boundary at alpha 0.05 for these hypotheses. Now let's read them. We're going to start with the alternative hypotheses first. This says that the mean of the population that our sample comes from is less than the existing population mean of 27. And the alternative the null hypothesis says that the mean that our population that our sample comes from is greater than or equal to 27. That's all the other possible events if it's not less than. All right, so let's think about this. I think that my sample mean is going to be less than 27. That means I think that my sample mean is going to be in the left tail somewhere. That's where I'm proposing. So I know I'm going to have a negative critical boundary because I'm looking in the left tail. I'm expecting my mean to be less. Because it's a one-tail test, we're putting all of the alpha in one tail. So 0.05 is in one tail. What we do is we look at our z table for 5% in the tail, and lo and behold, we end up with 1.65. But since my proposal is that my sample mean is going to be less than the population mean, my critical z value is a negative 1.65. That's going to be the critical value that my mean has to be more extreme than in order to reject the null hypothesis. Let's try another one. Find the critical boundary at alpha 0.05 for these hypotheses. And in this case, we have, let's start with the alternative hypothesis. The mean of the population that my sample comes from is not equal to 52. Or the mean of the population that my sample comes from is equal to 52. I know just by looking at equals and not equals, I'm now dealing with a two-tailed test because I'm just going to say that either it's equal to or it's not equal to. I'm not saying in which direction it's going to be. So in this case, I have alpha at 0.05, but it's a two-tailed test, so I have to split up that alpha into two tails, 0.025 in one tail, 0.025 in the other tail. If you look at your z table, 0.025 in the tail is equal to plus or minus 1.96. It's not a directional hypothesis, so we have to have the plus or minus. All right, one more. Find the critical boundary at alpha 0.01 for the hypotheses, blah. Let's look at the alternative hypothesis first. The mean of the population that my sample comes from is greater than 17, which is the population mean, or the null hypothesis is that the mean of the population that my sample comes from is less than or equal to 17. Okay, so what I'm really saying is that my sample mean is going to be greater than 17. So I know that I have a directional test. I have an arrow here, right here. So I know it's directional. And the direction that I'm stating it's going to be in is positive. I think that my sample mean is going to be greater than the population mean of 17. So I'm going to be looking for a positive value. It's a one-tailed test, so I'm loading up all of the alpha in one tail, 1% in one tail. The z-score that's associated with 1% in the tail is 2.33, and my critical z is positive because I'm saying that my sample mean is going to be greater than 17. Okay, we're going to actually do one more. Results of a one-tailed hypothesis test produced a z of 1.79. That's my calculated z. And am I going to reject or fail to reject at pretty much alpha 0.05 and alpha 0.01? So let's think this through. It's a one-tailed test. So if I have alpha 0.05 for a one-tailed test, it's all going to be loaded in one tail. 5% in one tail is equal to a z of 1.65. So between 1.64 and 1.65, we call it 1.65. So if my cutoff is 1.65 at an alpha of 0.05, is 1.79 more extreme than that? It is. It's further out into the tail. 1.75 is more than 1.65. So in this case, I reject the null hypothesis. I reject the idea that my sample mean is just like the population mean. I say, no, it's different. So I do reject the null at 0.05. Do I do so at 0.01? Well, let's think about this. We're going to put 1% in one tail and look at our z-table for the cutoff. And the cutoff in this case is 2.33. That's the z-score that cuts off the top 1%. So is my z-score of 1.79 more extreme than 2.33? It's not. It's less extreme. So in this case, I didn't exceed. I'm not in the critical region. I failed to reject the null hypothesis. So in this case, the researcher rejects the null hypothesis with alpha 0.05, but not with alpha 0.01. Very interesting here. Depending on how I set my alpha, I have two different decisions. And so this is where alpha plays a big part in power. I'm more able to detect a significant result with an alpha 0.05 than I was with 0.01. I missed it at 0.01. All right, those are the videos for this week. I expect there to be questions. This is a lot of heady stuff. See me in the Hallway Conversations forum and we'll talk them all out.